So who do we have here today? So we have back Draft Science. Now what was your first name, real name?
It's Gary.
Gary. Should we call you Gary or should we call you Draft Science?
Oh, well, draft science sounds like a title, so I think I'll like that better. But Gary's okay if you're more comfortable.
Well, I think it'd be easy to remember Draft Science because we see your name on your on the prompt there.
Yeah, that's good for me.
I think we had some heated discussion last week about what Bill Lucas was discussing there.
Yeah, well, I tend to say what I think, and that can get you in trouble sometimes. But hopefully it won't get out of hand. Uh, David seems to have that's worn off, so he seems okay now. So I think we survived it. But yeah, I just don't. I guess I'd sort of like that as a conversation would be the subject of why people are so passionate about some of these things like ether, and because I kind of don't see as much. I see the same problem. I mean, the evidence is weak for Einstein and quantum mechanics, but the evidence is also very weak for ether. And I'm surprised how many people are etherists.
So, what do you think is the say the weakness of quantum mechanics? If you could point out some things.
Well, it's like see, Einstein doesn't explain gravity in the sense he provides no source of energy, and quantum mechanics does the same thing to, like, say, magnetism, for example. There's absolutely no source of the energy. Like, how do the magnets move together? What fuel gets burned, for example? And there's no explanation for the fuel that gets burned. It's just this virtual something or other that somehow does this thing. So they don't even, Einstein has a fake medium in the sense of bent space, but quantum mechanics doesn't even have a fake medium. It doesn't have anything. It just has this, and then the rest of it's just wave theory. And I would argue that that's angle theory. It's not wave theory. Maxwell's equations are all about angles. It's not about waves. And so,
Well,
that.
is quantum mechanics even supposed to try to explain that? Because it seems to me that a lot of modern science, the philosophy is, well, if you can write an equation that explains the empirical results, you're done, right? So,
Yeah, well, I think that's sort of what quantum mechanics is. I mean, quantum mechanics is basically everything smaller than the galaxy, right? I mean, anything smaller than a planet is all of a sudden affected by quantum mechanics, and everything above, like an asteroid or whatever, is, Einstein. So it's like, to me, that's how I make the delineation is quantum mechanics is claiming that every single particle, an atom, 10 atoms, 100 atoms, all have this quantum mechanical Heisenberg blah, blah, blah problem. And it's just smaller with the big things than it is with the little things, so we don't notice it. But everything somehow has a quantum mechanical property, and that has something to do with why it doesn't move from point A to point B in a straight line sometimes. But like I said, it's a very ambiguous quantum mechanics. I mean, it doesn't, every person you ask, every physicist will give you a different definition of what quantum mechanics means. I mean, Feynman, for example, wasn't a Heisenberg-Huygens person. He really he didn't believe photons were waves, and he didn't think of it as wave interference. He just thought of it as a random number generator was imposing on photons and telling them, you have to do this probability math. And so he didn't account for causes at all. He just kind of said, I'm not even going to deal with a cause. It's just a probability equation. And so he wouldn't even fit in the traditional, that's the funny thing, right? He's known for being a patriarch of quantum mechanics. And his definition wasn't anything like the most popular definitions.
yeah, I've always found that to be, whenever I want to make a reference for something that's extremely vague, it's like, I would say quantum mechanics, because who knows what that really means, right?
Yeah, and
It's
they
so
even,
vague what they're talking about.
when they go into the argument admitting nobody understands it, I mean, that's not a funny joke. You know what I mean? When you're going to go into a courtroom and say, you're not going to believe the evidence I'm going to present, it's going to sound totally insane. That's starting your trial, in a very negative position, in my opinion. When you're admitting people can't understand what you're saying.
Let's see, I've got the wiki here saying that quantum mechanics is a fundamental theory which describes nature at the smallest scales of energy levels of atoms and subatomic particles. At least that's what wiki says.
Yes, well, they've also included buckyballs now and other, atomic structures. So they've moved the quantum mechanic experiments to bigger and bigger objects. So now they're claiming bigger and bigger objects have these quantum mechanical properties.
So by this definition, quantum mechanics is anything that's small.
Yeah, that's pretty much what I would have said.
So they're mentioning things like transistors and semiconductors and
Yeah, well, that's just Maxwell's math. So they're claiming that Maxwell's math is quantum mechanics, but you really just need Maxwell to do most of the conversions between photons and electrons. That's the old style electrodynamics. That was around before 1930. You didn't really need quantum mechanics to eventually make a transistor. I mean,
do you think when they're making a transistor, they're even thinking about any of that stuff?
No, I made that argument. I worked in a machine shop, and we were always inventing by blowing things up. Let's try this. Let's stick the electrode in our ear. I mean, you try anything sometimes to get something to work, and so there was no theory. There was just you knew it did this, and you're saying, well, if it does that, it must be able to do this too. So let's try to make it do this. And so I think that's where invention comes from. I think most invention is as the Edison style, not the Tesla style invention. Most of it's just trial and error.
Well, there are always these claims about, quantum mechanics is the basis of, modern society, blah, 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 blah.
Yeah, well, they don't have any evidence. They just say it, right? So, if you ask for evidence, they don't have the evidence. They cite the integrated circuit, and I could just cite how the first papers written on the integrated circuits didn't mention Heisenberg or Huygens or any of that stuff. So you can say it was quantum mechanics, but no, it was just the knowledge that there was this effect, and that you could create essentially a vacuum tube out of a solid state material, and it was all incremental. It's not like they went from vacuum tubes to integrated circuits in 4 days. It did take them years to slowly improve their new light bulb, so to speak. Look how long it took to get to blue LEDs, 35, 40 years, from red LED to blue, 40 years.
Uh-huh. But man, after that happened, then progress was quite rapid. Now we have LED lights for like everything.
Yeah, I mean, there was always, they knew theoretically it was there. I mean, even back when I worked, 25 years ago, 30 years ago, LEDs were a little bit expensive, but the great thing is they lasted a really long time. So they're really great, in industrial purposes. But you knew you were losing a heck of a lot. You know what I mean? The amount of energy, the light you were getting was very small compared to the energy you put in. So you knew there was huge efficiencies to be built out of that. I worked with some of the first diode lasers, and they would cost us $40 and they'd last 6 hours. And now they last 40 years and cost 4 cents.
I wonder if they credited quantum mechanics with the development of the blue LED.
Oh yeah, they do. They think quantum mechanics is the photoelectric effect. They think photosynthesis in plants is quantum mechanics. They bend everything to their model, and I suppose that's natural. But the way they claim that it's evidence of their model is the part that I find irritating. To claim you can explain it with your model is one thing, but to claim that every single thing that manifests a sine theta angle is therefore proof of quantum mechanics. I mean, that's the part that's just so irritating.
So they're claiming here in this article it has something to do with the band gaps and things like that, although I don't see any direct attribution to quantum mechanics here in the history of blue LEDs.
Yeah.
But you say like one of your main objections here is that neither quantum mechanics nor Einstein's relativity explain things as fundamental as like the power source for gravity and magnets. Now I've always thought that to be an interesting question.
Well, it's a huge, when you think about how big an absence that is, a deficit in their theory. That's a huge deficit when you think, of how much energy it takes to move galaxies and move planets and move suns and move all of these big celestial bodies. And they're not accounting for any of it, none. It just comes from the magical bent space energy factory, and you don't have to have a force, and you don't have to have because everything else, all other forces require us to fuel the force. We have to do something to force the explosion or the expansion, and we can account for why it exists. Like we know the atom is compressed, and if you uncompress it, okay, that's nuclear power. We can figure out where the energy comes from, but they don't have it for the two most important things, gravity and magnetism. Neither one do they have an explanation of what burned the energy. The Earth didn't get lighter. The sun doesn't get lighter from, it gets a little bit lighter from emitting photons, but doesn't get lighter by producing gravity. So where does the energy come from? And they don't have an answer.
Well, what about you personally? Have you heard of any plausible answers to that question?
Yeah, well, I think the plausible answer is my theory that it's a particle force. There's one force, and it's coming from the outside in. So like the cosmic background radiation, there's little tons out there, little bits of energy, and they're all moving in random directions, and that essentially equals an even pressure on everything. And in that pressure field, when two things get close to each other, they will in a sense shadow each other. It's sort of the wrong way to say it, but they shadow each other, and they create less pressure between them because it's a straight line force and nothing bends around. So that's what creates what we call attraction, which is really two things being pushed into each other, not two things being pulled into each other. But that explains it, in my opinion, quite well, because it also explains magnetism.
So that's more of a particle type pushing theory.
Yeah, it's definitely part. I think photons are particles. I think everything's particles. Yes, I mean I think all the forces are all the things moving the speed of light are a discrete little particle moving the speed of light, and it's either at a frequency or it's polarized. But there's no other. Gravity would be unpolarized, light would be at a frequency, and magnetism would be polarized. And so with those three different variations on the same force, you can create most of the stuff we see happening.
Okay, so I think but for dissidents, I think it's fair game to say that your theory probably should answer that question. I think in our upcoming conference we're having a Grand Prix, and I think one of the questions is, what is gravity? And I suppose, it's not just the equation of what the force of gravity is, but, what exactly creates that thing, what mediates it, what powers it.
So that's the great thing about the external particle model, is that it duplicates the inverse square law perfectly. So it even not only does it explain where the energy comes from, but it's the exact way you create the inverse square law. Because if you think about a light bulb emitting light, that's the inverse square law. It's basically the idea is you're emitting a force spherically in 360 degrees, and that's why the force gets weaker as you go more distance, is because all of the rays are diverging at the inverse square law rate. And so so a particle gravity would be exactly the opposite of a light bulb, in the sense that everything would be moving in towards the thing it's going to hit eventually. And it would perfectly duplicate the inverse square law. So that's another winner for it. Not only does it explain where the energy comes from, but it's exactly it's a perfect mechanical model for the inverse square law.
Now this would require the particle that's causing the gravitational effect travel all the way from one place to another. Wouldn't
Yeah,
that?
there's no instantaneous action, so yes, nothing moves faster than the speed of light, in my opinion. So yes, all the forces move the speed of light.
So you'd actually have to have a particle traveling from, say, the Andromeda galaxy all the way to the Earth in order to exhibit its gravitational influence.
Well, it's the same with photons. Yes, to see Andromeda, we have to see very old photons, ones that have been traveling hundreds of thousands of light years, so millions in some cases.
But do you think that that photon is an actual physical particle, like has mass, like a marble?
Yeah. That has to. That's why it has momentum. That's why it can impose an effect. That's why sunlight can move things. I mean, all the forces move things, and they move them because they have to have mass, in the sense that they have to have some way to impart their momentum. So their momentum it's absorbed. It's not reflection. Reflections are an absorption, by the way. But anyway, the force is basically captured. The little bit is captured inside the material object, and now the material object moves obviously much slower than the thing that went into it because it's much smaller. And so if you divide
so my question to you, though, as a critic, would be: don't you find it a little bit hard to believe that a physical particle could travel that amount of distance and not be perturbed? Like if I fire a physical bullet, that's definitely got a limited range.
Well, I know, but if you fired it from space, at the moon, it would get there. It would go hundreds of thousands of miles to the moon with no problem. So, I mean, this stuff goes forever in space once it's not being perturbed by any particular gravitational field. Once it gets going, material things will keep going. Now, the force bits keep going because they're force bits. I mean, they always go the speed of light. They never slow down. So they never do anything but go in a straight line at the speed of light.
Well, here's the problem I have with that. And that, if they are particles, then we know by Newtonian mechanics that, when two particles collide into each other, they change direction and they get scattered.
Well, I know, but like I said, you have to make simple rules that the force bits can never hit each other. So,
that's impossible.
Light never interacts with light. Photons don't interact with photons. The nuclear forces magnetism forces don't interact with magnetism forces. The forces never interact. The force only affects a material bit. So electrons and protons.
Well, think about that statement. You're saying that the particles never interact with each other.
Well,
is that logical?
Let me put it this way. There's two kinds, right? So they're polarized. So I don't want to make a complex distinction. But if you think about it kinetically, so think about a letter X, right? And think of the bottom part of the X, the two little lines coming in. So think of that as two things intersecting, right? So two little bits are coming in to intersect, right? Do you understand me so far?
Yeah, and they will collide, and they will.
Right, and when they collide, then they'll leave in the V pattern. Now, if I don't make the two things that collide a different color, you can't tell whether they reflected, whether they went right through each other, or if they missed entirely. Every single one of those universes look exactly the same, right? If they missed each other,
very, very specific. I mean, they would have to come in at exactly the same energy.
They're always the same energy, the same speed. No, just get me wrong. They're moving the same exact speed. They're the same exact particle. So I'm saying in a purely kinetic interaction, just think about it for a minute. All right? Like even think about a head-on collision. How could you tell whether the two things hit each other or went past each other? How could you tell whether they hit each other or missed each other? By just looking at the before and the after picture.
Well,
It's
perhaps you wouldn't
impossible.
be able to tell.
It's impossible to tell. That's right. If they're the same color, if you don't make some distinction, some way to tell, you can't tell whether the universe looks exactly the same if they hit each other. It looks exactly the same if they miss each other. So my point is I'm just saying, for all intensive purposes, force doesn't interact with force because its interactions will always be invisible. They're just the same as misses because it's purely kinetic. Two things go in moving the speed of light, two things leave at the speed of light. There's no proportional differences, there's no anything. So it'll always end up just being this, what goes in is what comes out, and it's always going to look the same as if they missed.
Okay, well, I think I understand your argument.
So
Although,
the tricky,
is the particle that you're talking about, is that something that we can really relate to in mainstream science? Would mainstream science give it a specific name?
well, like I said, it makes up a photon. Two of them at a frequency is a photon. Two of them polarized, like that is, I mean, not two of them, any number of them, but segregated by a magnet. A magnet basically tells the red ones, there's two kinds, there's proton force and electron force. And the two are on different levels, dimensionally, so they don't interact directly unless they hit matter. But that's a more complex thing. But the point is magnets segregate the two colors. So all the red force, the proton force, goes out one end, all the black force, the electron force, goes out the other end. And that's why magnets basically just filter the force. So yes, the force is in magnetism, the force is in photons, the force is the nuclear force, and the force does create gravity. The same little bits do it all.
Although the bits you're talking about, the two bits that make up the photon, are as of yet an undiscovered particle.
Well, I don't think they're at all undiscovered, so that's kind of bizarre statement, actually. I don't know how we can make it more discoverable. They impact electrons, they crash right into them and move them. So I think it's quite obvious that they.
Well, undiscovered in that there's no experiment that has shown that they exist independently. You know, like they like electron or positron
I
or
don't know. What's the
neutron.
difference between those experiments? Do you want to give me a distinction between the experiments that prove an electron and the experiments that prove a photon? Because
Well,
frankly,
one thing that I guess Bill brings up as far as making a distinction is that you can create a beam of these things. So we can make a beam of positrons. We can make beams of protons.
Well, look how far they go, though. You can't make a. Well, I don't even agree that positrons exist, so I can't. I'm not going to argue whether you can make a beam of them. But an electron beam won't travel through space. If I shoot one at the moon, it won't get to the moon. So you can say that you can make a beam out of them, but you really can't, because once the voltage stops, they die very quickly. I mean, is it alpha radiation? That's the electrons. Alpha radiation only goes what, 3 inches? Or is it beta?
Yeah, that was kind of the basis of my question is like we can create these beams of particles and they don't go very far. So how could that possibly be any kind of force carrier?
Well, I'm just saying I don't think it's a standard for the difference. The difference, in my opinion, are there's things moving the speed of light, and then there's everything else. So in my opinion, that's the distinction. The force always moves the speed of light in its smallest elemental form, and the matter bits obviously don't, because they have to combine a whole bunch of little different speeds and have a net speed. So they're full of those little force bits. So for example, and those force bits will decide which way they go in a net way. They'll have a net amount of them in a certain direction. So like when the space shuttle's taking off, what's basically happening is there's a huge amount of force going one way out the tail, and there's a whole bunch of force going inside of the shuttle that's staying in there in the opposite direction. And that force doesn't leave until it interacts with another piece of matter that says brick wall or something, and now the force gets released. But the force goes into the shuttle. It collects the little bits moving the speed of light in a direction, and its net velocity is a byproduct of what it collected. So it collected energy in a direction, and if you give it some energy in another direction, it'll do the math and figure out it's supposed to go this way. You'll have a new direction, a new net direction.
Well, kind of playing the devil's advocate here, I would say that what do you think of the mainstream's interpretation of the situation? Now, your interpretation is that a photon is a physical particle. It is traveling from A to B. But I would
Feynman's. Let's just remember, it's also Feynman's interpretation. Feynman was very explicit in saying, "I wish I could go to colleges and tell kids not this wave stuff isn't true." And he agreed with Newton's description of the photon as a corpuscle. So clearly, Feynman thought of it as a particle.
Well, I guess that's one of the major disagreements, which is, what is the nature of light? The whole thing about quantum mechanics is light a wave? Is it a particle? Now, mainstream has this tendency to say that they're both.
Yeah, well, if we agree that both is silly, then we're stuck with, what's the evidence? And my argument is even Maxwell's equations, they're not wave equations. Schrodinger's equation is not a wave equation, it's an angle equation. There's a sine theta in the equation, which means an angle. It's an angle. It's not a wave. So there's no waves in the equation. There's just an angle change. So the two-slit experiment is made by an angle change, not a wave.
So you would argue strongly against the wave interpretation.
Yeah, I think waves are in the ocean. They're not. You need a medium for waves, and there's no medium. So yes, like I said, that's this ether argument. I don't think there's an ether. So everything is, there's nothings and then there's somethings. There's this force is real stuff. It's a something. It's not a nothing. And there's no medium that everything's traveling through or swimming in.
Well, I would bring this up because it's like we can get that 1 over r squared characteristic in one of two ways. Either you have like a sphere and there are particles emanating out of that will obviously drop off as 1 over r squared. But although it's not that tough to get 1 over r squared, it could also be if you have a sphere in a medium and it's generating a wave, then that will also be 1 over r squared. So how
does it produce 1 over r squared, a wave? Because wouldn't a wave be spreading and it would be continuous? And how does it do the r squared part? It's not rays of anything. I mean, rays do the r squared thing.
It geometrically decays as to the surface area of the expanding sphere of the wave. So it starts out with a certain amplitude.
Yeah, well, I know, but aren't you really then just turning the wave into something that breaks into rays? I mean, you're kind of degrading it by saying it doesn't spread anymore. Once it goes a certain distance, it starts to lose its spreadability or something, or it breaks into little pieces.
No, it loses its amplitude. I mean, if you were to measure the pressure wave, the amount.
Okay. Then I would argue to you for that argument that then we go back to the Einstein, problem, and Feynman's argument that when you measure photons and other bits, they don't measure as a reduction in a wave. It's either a complete corpuscle of energy, a Planck constant, or what's the word they use for the quantum, like with the energy levels in an atom, there's a certain quantized amount of energy to get from one level to the next level, and it's always the same amount, and it doesn't vary, and it doesn't get, you can't do a half a one, you can't do a quarter one. So there's clearly no analog. It's clearly digital in the sense that it's bits of energy. So the evidence clearly indicates that you can't have a weakening wave, because the weakening wave won't create the quanta of energy. It'll create a half a quanta or a quarter quanta or 1.5 quanta, and it's not allowed to do that. I mean, it's not allowed to fit the evidence. It can't do that. It has to do something that's in clumps. It has to clump, as Feynman would say. And you can't make a wave clump.
You could make waves. Well, it's what quantizes the energy is the energy level. Now, because classically, those energies can exist at any level. But this is kind of the quanta in quantum physics.
Well, I'm just saying that let's just say the Einstein photoelectric experiment is a valid experiment. It's pretty simple. It basically demonstrates, though, that you need like 5 thingy. You know, you need a certain amount of stuff to do a certain thing. Okay, so you need a certain quanta, a clump of energy, and you can't have something variable, that is, that goes from 1, 2, 3, 4, 5, that has a whole bunch of variance. It has to have clumps of 5 and then 10 and then 15 and then 20. So a wave isn't going to do that. A wave is analog. It's going to create this, you know, very subdividable amount of energy. It's not going to do the clump thing that it needs to do, which is it needs to deliver a specific amount of energy no matter how far away it is. So when the photon hits a frog's eye, for example, it's one clump of energy, whether the frog is 1,000,000 miles away from something or 1,000,000,000,000 miles away, or whether he's 2 feet away. The clump of energy is always the same. It's just you get less clumps. So the trick with photons is if you want to have less light, you have less clumps. You don't make the light dimmer. You just shoot less photons. So, you know, that's how lights are dimmed, is you're just turning down how many photons. You're not making the photons weaker or stronger. You're not regulating a wave. You're deciding how many clumps you're sending.
Well, I think that is a very distinct property of photons, which gives them this kind of particle thing. I mean, one of the pieces of evidence that we have is that when you do photon, electron, positron annihilation, you get 2 very distinctly detectable gamma rays. And those gamma rays, you know, they hit the detectors like bullets. You know, they only detect them in actually 2 places. So this is why, you know, they think that these gamma rays at the very least come in very distinct packets. Now, if that energy was
gamma is just photons. So right. So
yeah, it's just photons.
Yeah. So it's just another way of saying it. You're just creating a high frequency light. So yeah, there's no surprise there, in my opinion. But I do have a problem with the whole annihilation idea. I don't think any such thing happens in the real physical world. And I think Susskind sort of, you know, from California there, you know, he describes it as, you know, the idea of the antiparticle as really the vacancy created. So when something leaves a spot, like when an electron leaves an atom, it's left a vacancy behind in terms of a pressure vacancy. And that's really the antiparticle. The antiparticle isn't like a real particle. It's just the fact that you now have a pressure vacancy somewhere in the system. So every time something is out of a system, somewhere in the system, there has to be a hole that it came out of, so to speak. Like everything that's a positive bit of energy, you could think of it as being like a golf ball that popped out of a hole. And now there's a hole where the golf ball has to, you know, fit back in again, or a golf ball can fit back in again. So I think I'm just saying that by him using those kind of metaphors and analogies, I think they're kind of conceding that they're using words that aren't very explicit, that these antiparticles may not actually be physical particles, just like the anti-electron wouldn't be just like an electron, except in every way upside down and backwards. You know, it wouldn't be like an inverted particle. It wouldn't be a particle.
Well, what do you think an electron is?
I think an electron is just I call them matter bits. There's 2 kinds of matter bits, protons and electrons. They have the charge. They filter the force. So the electron force bounces off electrons. The proton force leaves perpendicularly. Vice versa for the proton. So but they're just there's 2 forms of force. There's 2 forms of matter. So there's proton force, electron force. There's electrons and protons. and that makes charge. The fact that they interact opposite with each other, they affect the force in exactly the opposite way, protons and electrons, and that's what creates magnetism and charge and electricity and all of that. So I don't know how else to distinguish them except to say the matter bits don't have any inertial movement. They don't have any innate velocity. They can only have velocity while they're being accelerated. So they have to be pushed by a force to move. And once you stop pushing them, they stop moving. Where true matter, like atomic matter, you can push it and it'll keep going because it captures these little force bits. But an electron and a proton can't capture very much for very long.
Are you postulating those matter bits? Meaning that, you just have to accept that they exist.
Well, I'm postulating in the sense that I think it's well established that the basic function of atoms is protons and electrons. And it's perfectly consistent with my theory that they would exist. So, yeah, I'm postulating the existence of the difference between force and matter. The matter is one thing, the force is another thing, and they interact with each other where matter doesn't really interact with matter and force doesn't really interact with force. Matter only interacts with force. So if something's expelling a force, then the matter will bounce off. It's like two electrons never really hit each other. They just bounce off of each other's charge. So the one is radiating like little bullets, you could say. It's radiating little bullets. And the other one's radiating little bullets. And they happen to be the kind of bullets that bounce off. That means they reflect, which means the thing moves in the opposite direction. So they are basically extruding a repulsive force at each other. And that's what they bounce off of. I
got a question, Franklin.
Yeah, go ahead, Harry.
Sure.
I have no idea what this guy's talking about when he says force. What's a force? Tell me what a force is.
Well, I guess I'll let Franklin do it. I think you do it now.
I'm asking you.
Oh, okay, it's fine.
You're the one who's been using the word.
Okay. Let me answer the question.
You've been using this word, and it's just an ambiguous concept.
Well, to me, it's a really fundamental concept. The force is all the stuff moving the speed of light. So if you find something that moves the speed of light, it's a force. Matter never moves the speed of light, can't move the speed of light. Only forces can. So, and that thing that moves the speed of light, I'm arguing, is an actual thing, like the cosmic background radiation, like all the light we don't see, like all the radio waves we don't see. That's a real thing.
You're not really answering the question. You're just speaking in riddles.
Oh, I just call it a thing moving the speed of light. It's a discrete particle that moves the speed of light. Is talking in a riddle. Okay.
So you're saying a force is a particle that moves at the speed of light?
Yes, that's what I'm saying.
Okay.
I find that kind of odd and disconcerting myself.
Well, I know, but you're ether people, so that's why you find it odd and disconcerting, right? I find it odd and disconcerting that people would believe there's some ether swamp or something that everything moves through. It just doesn't.
Well, it sounds like you have a prejudice.
Well, it's not that I have a prejudice. I just can't imagine it. I can't imagine how that's physics, how that's making something simpler.
Well, I can't imagine that there would be an existence of nothing. You're saying that part of the force thing moves at the speed of light through nothing.
Through empty space. That's right. There's stuff that is something.
Now, you guys got to let.
And there's stuff that's nothing. I mean, we invented the word nothing because we did get the idea that there's this concept of not.
So why does it move at the speed of light? Why the speed of light?
The fact of the universe. I didn't invent the universe. The universe is going to have some basic laws, like why are the red checkers? You can ask why are the red checkers red? Okay, and I would answer the question because somebody shows.
I'm asking the questions. You cannot tell me. You're saying that this thing moves at the speed of light, but you can't tell me why it moves at the speed of light.
I'm saying there's questions about the universe that you'll never have an answer to. So yes,
so you're basically saying that your theory basically has no explanation for why.
Well, I'm sorry. If I told you the universe was a giant checkerboard, and it has made out of red checkers and black checkers, Yes, you would have to just take it for a fact that, yes, we're never going to figure out who made the checkerboard. That's right. There's no God, and the universe might be infinite. So I can't tell you where the checkerboard came from.
Excuse me. I counter your argument that there's no ether by saying the universe has, because the universe says so. The ether exists because the universe says so. That's basically your argument. Counter argument is the ether doesn't exist because I say so.
No, I'm saying I have evidence supporting the theory I'm arguing. Okay, and the idea of wave particle duality wasn't invented by me. It was invented by the evidence. So this idea that these force bits could be bits, actual somethings, actual corpuscles, as Newton and Feynman said, seems perfectly reasonable to me, and that's why I believe that. Yes.
Well, but you're just making things up, though, as you go along.
I'm sorry. I don't, that's your accusation. I don't even know how to respond to somebody who said, I'm making it up because I'm giving you an explanation. I explained it, and that's making it up.
Just a minute. We can't hear what either of you guys are saying. I'll have to insist that you at least wait for the other person to stop, okay? So that we can, because when you're both going at the same time, we can't hear a thing, okay? So one person at a time, please.
Go ahead.
So go ahead, draft science. Go ahead and make your.
My contention is that your concept of force is basically not really scientific. It's just something that you made up because you can't explain why it moves at the speed that it moves at.
And neither will anyone ever explain why anything moves, what speed it moves. You will never explain it.
Well, that's just,
you don't explain it, do you?
Excuse.
Well, what's your explanation for the speed of light?
I explain it.
Okay, go ahead.
So I'm, of course, as an etherist, and I explain the speed of light as the speed of the wave through the medium. Therefore, you explain the speed of light as the result of the properties of the medium. And now we etherists have done calculations saying if you have this positron electron C, given the known electrical properties of the electron and the proton and the properties of permittivity and permeability, we can calculate what the speed of light would be from first principles. And we find out that it is equivalent to the measured speed of light. And that also does other things like the speed of light can be variable depending upon things such as the density of the ether. So the speed of light to an etherist has a very distinct reason for why it is that speed. It's just like why is the speed of sound through water.
I don't see how that's any more of an explanation of why it is that particular speed. You've just basically told me you're confident because you've given the ether a thickness, a viscosity, and therefore this is how fast something can move through it. But you haven't explained why. He's asking me why are these little bits moving the speed of light? Is the same thing as me asking you why does the ether perturbate? How can you explain to me why the ether perturbates?
We explain it exactly the same way we do in hydrodynamics. We can explain the speed.
Okay, never mind.
I mean, that's how we explain it.
It's like a declaration. You're not explaining it. You're just declaring it.
It's not a declaration.
All right, says you, I say. But okay, fine.
I mean, am I declaring, if I ask the same question, what determines the speed of sound through air? Do we have an answer to that? Or is that a declaration?
It's a declaration to say why the speed of sound is exactly what it is, unless you start talking about how big atoms are, because really that's the reason why the speed of sound is the speed it is because of the size of the atoms it's traveling through. So there's a clear relationship between the size of the atoms and how fast sound will travel through different mediums. We're talking about an ether. We're talking about a universal medium, not a medium that you can change like sound. So you're saying that you have a perturbation speed through this ether, and you're saying you have some reasoned explanation why it happens to be the speed of light. And
yes,
all you're really saying is that's what ether does. Ether makes things move the speed of light. You're not explaining any more than I'm explaining by saying photons move the speed of light. How is it different for you to say ether perturbates at the speed of light and for me to say photons move the speed of light? How are those two statements, one's incredibly less credible than the other?
Because I can precisely calculate what the speed of light should be, and it could be a different
so can
value.
Maxwell. So can Maxwell.
And that is all still probably all based on, the thing is that your permittivity and permeability are very similar to your things such as density and modulus of tension is what that is. And those two things determine the speed of sound through any medium, say whether it be a steel bar or water or air. It's a mechanical explanation.
Exactly, because we're making the medium out of real atoms. So we're talking about a real thing that vibrates. The real atoms vibrate. So that has a real mechanical explanation. You don't have a mechanical explanation for the ether.
Yes, we do.
What? You don't have any. You don't have any mechanical explanation that's any better than me saying there's really just particles moving the speed of light. Why do I need an ether that perturbates at the speed of light? How have you demonstrated the existence of the ether perturbating being any more credible than the argument that photons move?
Once again, you don't have an explanation for why the speed is.
All right.
You
well,
don't.
I'll just leave it to the audience. I'll leave it to the audience to make their judgment about whether or not these two statements are fundamentally different. Ether perturbates, photons move. They say one, I say the other. They say my answer isn't good enough. They say their answer is great. I don't think they've demonstrated any distinction.
Well, then you have to answer Harry's question, which is why is the speed of light what it is? Your answer is because it is.
Why? Because that's the way the universe is made. That's what the universe is made out of. It's a checkerboard. It's made out of physical things. You're never going to have an answer. So you can pretend that you have an answer for why there's an ether, but you're not going to be able to answer why there's an ether. Why is there an ether?
The question is, the better question
I'll
is,
revise my question. Let me revise my question. I want to know why the force doesn't move at infinite speed, because it's moving through nothing. So there's nothing to tell it how fast it can move.
Exactly. So the universe has, I just said it as simply as I can.
1% at a time, please.
Okay, well, it keeps going. All right, go ahead and make a longer sentence out of it.
I'm asking you to explain. Okay, my thesis is that if space is an empty nothing, then this particles of force, as you call them, should move at infinite speed. Why don't they?
Why should they move at infinite speed? Why should there be any rule about how fast the little bits move?
That's how you argue. I don't like this whole thing. You turn everything around and say, I'm not going to answer your question. You have to answer my question.
Well, what do you want me to say? God said so? You really want me to say that? God said so. God made it so. That's how he made the universe. He made things that go distance, and when they travel distance, it takes time. Now, whether it goes the speed of light or whether it's some other speed, it doesn't really matter. We wouldn't be able to tell the difference. If you change the constants, you change everything else. So if the speed of light doubled tomorrow, we wouldn't even notice it because everything would double.
Well, okay, I got it. God legislated it to be so because
I did that in satire. That's right. I said,
that was satire.
Where did the universe come from question. You basically asked me, where did the universe come from? And how am I supposed to answer that?
All right. Franklin, I think that we should move on to another topic. This is going nowhere.
Well, I mean, to be fair, all theories they ground out somewhere, right? At some point, you have to say what your postulates are, right? Now, and it's just a matter of where they ground out. I mean, a lot of dissidents will invent particles, let's call it, say, a circulon, whatever, and it's quite common, draft science is saying there's two things that make up a photon. For me, I would say that my theory grounds out at positrons and electrons. And, so I cannot explain, at least I currently don't have an explanation for what on earth, say, an electron is. Although I would say the advantage of what my theory is versus what data science is that at least an electron is a mainstream recognized particle that we're familiar with. We know that we're pretty sure those things exist. So,
well, it's fundamental to charge. Let's just remember, you can't have charge without it.
I mean, if your theory starts out with, assuming that electrons exist, then I would say that's a pretty safe bet. I mean, even if you can't explain what an electron is,
I think I can. You're the depth. You want the creation moment. I'm saying I don't have any interest in creation. I want to just talk about what is. And I'm saying you have to take as axioms of my theory that there are these things called electrons. There are things called protons. Now, you don't want to accept their existence, then I can't have a really conversation, because yes, I'm just saying I don't know how they were created. I don't know where they came from. I just know they're fundamental elemental particles of matter. And likewise, there's elemental fundamental particles of force. And these are these bits, these little force bits that make up light and magnetism and gravity. And they existed just like the electrons and the protons. I don't have their origin paper.
Yes, well, that's my objection, because that is the quote unquote made up particle of most dissident theories.
Well, I don't think I made up any particles, and I take it as resentful, this double standard, because again, I don't see where you in any way given me the explanation for where the ether came from. Who invented
the ether? The ether in say my preferred embodiment is just a sea of positrons and electrons.
Well, where did they come from?
This is my first time coming.
It doesn't matter where it comes from.
Well, you're asking me where they came from, so I don't want the double standard. If I have to explain where electrons, protons, and photons came from, then I'm just asking you, explain to me where ether came from.
No, I'm asking you that you said that a photon consists of two subparticles.
I said it, yes, it's a frequency. Okay, so to measure it, it has to be two. That's right. So it's the same.
We have somebody who's trying to ask a question.
All right. Well,
yeah, this is Jack Kirkendall.
Go ahead, Jack.
First quick question. Draft Science, could you tell me what your name is?
I don't think it's important, but it's Gary.
Gary, okay. And my second thing is I'm very interested in what you're saying. It's not necessary that I have to believe or not believe in it, but did you cover your entire theory without all the interruptions? It's like last week, Bill Lucas got cut off every time he said something, and it appears this is happening to you. Did you finish talking about your theory? Because I have a lot of stuff that kind of agrees with a lot of things you're saying.
Yeah, well, it wasn't an intent for me to present my theory. We were just having an open conversation, and just me talking about it. I do plan on making a presentation video, a 20-minute one, going over my theory and then having you question me on it. Eventually, I want to do something quite perfect. So there's no misunderstanding.
I would very much like to see that, but let everybody go ahead. I'm done. Thank you.
Yeah.
Well, you do have your website. We can bring that up, and
yeah,
people can explore that.
I have another question.
I have 800 videos too. 800 of them.
I have another question.
Yep.
Is there a magnetic photon and an electric photon, and if so, what's the difference between them?
Now, both electricity.
Excuse me.
Oh, I'm sorry. Yeah, your questions always ask the question.
That's my question.
Okay.
Usually, the usual photon is the light photon, which, as we know, is a alternating photon that has a frequency.
I don't know that.
That's one kind of photon, and then there's a magnetism. Okay, that's apparently another kind of photon, and then there's electricity, which is apparently another kind of photon. Can you explain to me how that works?
Yeah, I have explained it to before in this room, but I'll explain again. Briefly. So it's all one force. Okay, so like the cosmic background radiation, it's all one force, except the real force has no frequency. So bits of it can have a frequency, and then we can identify it, and then it's on the electromagnetic spectrum. So everything on the electromagnetic spectrum is just the little bits at a frequency. Now, if you imagine the little bits as having two polarizations, that is two types, and one of them is reflective of electrons, and one of them is reflective to protons. And when the opposite force hits them, it just goes out perpendicularly, consistent with Maxwell's equations. So, so basically magnetism is just filtering the force. So there's a bunch of these little tiny bits coming from random directions all the time hitting you. And if you were a magnet, what's happening is, let's imagine them as black bits and red bits. So the black bits would be electron bits, the red bits would be proton bits. What a magnet is basically doing is segregating those two. So they come in all mixed and they leave, okay, all the red ones out of one end, all the black ones out of the other end. That means all the proton force out of one end, all the electron force out of the other end. Now, when you put that in association with matter that's capable of being a conductor, what happens is it pushes the electrons down at one end, and it pushes the protons down at the other end, which means it creates, it changes their magnetic polarity and causes the electrons to basically move. So you're moving the electrons with the magnetism, with the force being created by the segregation. So at one end, all the electrons are under high pressure. At the other end, all the electrons are under low pressure. And that's what creates voltage. So electricity is just a manifestation of magnetism, I would argue. It's not a separate force. It's just a byproduct of magnetism. So there's just gravity, magnetism as the two forces that are most obvious to us. And then you have the nuclear forces, which are basically just a function of the electron and proton interacting with each other as charged bits. So I would argue that the proton and the electron are the actual magnetic monopoles.
So by the way, do I have your Draft Science YouTube channel up here?
Yeah, you do.
So you're saying there's no such thing as an electric field, as I understand it.
There's one made out of these little bits. Yes, there's fields everywhere around us all the time, and it's all these little bits moving the speed of light.
That's not what I asked you. I asked you, are you saying there's no
made
such
out of
thing as an
particles.
electric field?
There's an electric field created by particles, little bits radiating, like a light bulb radiates photons. The same kind of radiation comes off of magnets, except it's colorized, so to speak, and polarized. And yes. So anytime you say there's a field, or you're really saying there's a force. And the force is made out of particles.
Okay, again, what's the difference between the magnetic field and the electric field?
The electric field is just a manifestation of a magnetic field. There's no distinction really. They're created by the same basic polarization of atoms. So when the atoms are all in one direction.
Polarization. I don't know what you mean by polarization.
Polarization of charge. That means the electron is at one, all the electrons are pointing one way, and you're all heads up, and all the protons are heads down. That would create a charge differential. That means, that's basically what's happening inside of a magnet. A magnet is a bunch of atoms, and when the atoms are lined up, each atom has a charge imbalance. And when you line up all the charge imbalances in the same direction, it becomes a magnet. Because it diverts force.
You still haven't answered my question about what is the difference between the electric field and the magnetic field.
I don't think I said pretty clearly, I think there isn't a difference.
Well, I think one difference is that the magnetic field is really distance limited compared to the electrostatic field, which is apparently infinitely.
No, I don't agree that there's any infinite electric field. And static, when you start getting into the movement of electrons, it's different. Okay, like a lightning bolt isn't photons moving from clouds to the earth. It's photons moving through ions in the atmosphere. So the atoms are creating a conduit, a pathway for the energy, the force bits to move through. So the force can't get from the clouds to the earth if it wasn't for the ions that allowed that to happen.
Well, I think the question that Harry asks is a very interesting one, which is what is the difference between the electric field and the magnetic field? I don't know if it's going to help you, Harry, but I can give an and I'll say my explanation of that. I mean, I have to explain that too. You could ask that same
Well,
question to me.
I'm more
similarly.
interested in his idea. And
Well, let's just admit that
I'm not really clear
the electric field is incredibly weak as a magnetic field. Could we agree on that?
No, I'm not agreeing on anything. I'm just trying to understand.
Okay. I'm just saying that they're
I'm
the
trying to
same thing.
understand
They're
a
the
couple
same
of
thing.
points.
One's incredibly weak magnetism and one's really strong magnetism. So magnetism is really concentrated magnetism. And the electric field is weak magnetism because when you move the electrons, you're lining them up and creating a weak magnet. So anytime electrons are moving, you're creating a weak magnet, and it creates a field that is magnetic, and it'll induce the same opposite effect inside of whatever conductor is next to it. So they're just magnetic fields that always create opposite, push-pull fields, that they're always tugging against each other. But the field created by an electric current moving through a wire is a really weak field compared to the field that a piece of neodymium can create. And obviously you can oscillate it. You can control electricity, so you can create an oscillating field where a magnet can't do that. But an electric field is just a magnetic field.
Well, what do you think of that, Harry? I would personally disagree. I mean, I would say you do have to figure out what an electric field, really is. And it seems to be something that is radiating away from a charge like an electron as 1 over r squared. And so I would distinguish that as being, I call it actually, it's just a high frequency electromagnetic wave.
Well,
that's what my theory says.
Could I just narrow the conversation a little? That it's a little hard to study because it's all medium based, right? So if I have a high, like a Venn diagraph, and I create a high voltage, it's completely dependent on the atmosphere for that high voltage to get anywhere, right? I mean, it has no going power unless I create an atmosphere for which it can travel through. So
no, that's not true. If you did a Van de Graaff generator in a pure vacuum, you would find that it creates a field which attracts the opposite charge. It's not relying upon any medium.
Well, it does require a medium to create a spark. To create a spark, it does.
To create a spark, well, even you can create a spark through a complete vacuum as well. I mean, the spark is an actual manifestation of physical particles going from one voltage potential to another.
You have to do that through the form of a plasma, which is very different. So a plasma is made up of the atoms of the anode actually being destroyed. I mean, the cathode. Anode. I was getting backwards. But anyway, emitting atoms, and the plasma is essentially a ball of gas through which the electricity again is being able to travel through. I wasn't trying to say that the Van de Graaff creates no effect on a charged electron. My point is that for there to be a transfer of electricity, there has to be a medium through which the electricity travels.
Okay,
Not
I got
necessarily.
some more questions. Got more questions here.
I mean, if you have an electron CRT, that is transmitting electrons from the back of the CRT to the front through a pure vacuum. So,
right, but that's not that's moving electrons. I was talking about the force traveling through. So that's just a voltage pushing electrons.
Yes, that's
very high.
And that is generally what an electrical discharge is.
Well, I know, but that's not exactly the same as charge. But
that's completely different. Now, Harry, did you have a question?
Oh, I got another question. So as I understand what you're saying that magnetism is the primary manifestation of the force of electricity. Is that part I'm not really clear. You might want to clarify some of the terminology there. Is that correct? You're saying
I'm saying
electricity is a sort of a manifestation of magnetism?
Yes, electricity is the idea of moving the electrons, which I'm not exactly sure they actually move, rather just vibrate and transfer the force. But the point is the movement of the force is what we call electricity. All right, these little bits moving through a wire, and they do it through the electrons. It's the electron force, and so that's what's moving is the electron force. So I'm making that clear distinction. But the real important point is yes, it's more magnetism because the whole charge phenomenon is created by electrons and protons. Now you could say that that's electric, but the point is its most obvious effect is magnetism. It creates this ability to filter the force. That is, the force comes out of one end of the atom one way and it comes out of the other end of the atom another way in an imbalance. So that is, it's proton force at the bottom of the atom and electron force at the top if that's where the electron is. So the point is that's what creates the mechanism that makes everything else possible. So I guess I would say that yes, magnetism is the fundamental force and electricity is the byproduct. You could make the opposite argument that electricity is the fundamental force and magnetism is the byproduct, but I'm just saying one of the two forces, they're both so tied to each other that they're the same phenomenon. They're just different manifestations of the same phenomenon. So I'm not glued to which one you want to pick. If I was going to answer the question, I would say that magnetism is the more fundamental function, and therefore.
Right. Well, you've confused me now completely and totally. I wasn't talking about electricity. Your definition of electricity seems to be electricity that moves in wires that comes from the electric company. I wasn't talking about that. I was talking about the electric field, which is the static electric field.
Yeah, and that's created by
some kind of a bit of confusion of terminology on your part.
I don't think so. I mean, I think I made it clear that electrons create that static charge, the difference between the exposure of protons and electrons. If the exposure on the surface of something is more proton heavy than electron heavy, it has a positive charge. If it has more electrons on its surface than protons on its surface, it has a negative charge. So I don't think I've been inconsistent at all.
I have no idea what you just said.
Okay, you don't understand that it's the density of electrons and protons that basically dictates the charge, the static charge on any object.
Well, that's obvious.
I'm
Did
not
that
sure
answer your
that's
question?
not what I asked you, but I want to know the difference between the I mean, it seems to me you're claiming here, from what I've been listening, I mean, you're saying that photons exist, and you're saying the ether doesn't exist and waves don't exist, apparently. Not real clear on these points. And your main claim seems to be that you started off with by saying that light is a photon, it's a particle, okay, or corpuscle. And my question then, that the form of my question is, if that's the case, then how does a magnetic field, okay, because we're talking about, light is a photon, which is this oscillating high frequency effect. And then you have an electric field and a magnetic field, and the theory says that electric field and the magnetic field make up a wave of light, but you're saying that light isn't that, it's a photon. So I'm wondering, what is the electric field and the magnetic field, and is there a magnetic photon and electric photon?
Well, okay.
Have a magnetic field and an electric field and an oscillating electromagnetic field.
Yeah, I don't think there's any evidence that photons are electric or magnetic. You can't move a photon with a magnet. You can't do anything with it electrically. They're not made of. The electromagnetic spectrum is only a holdover from Maxwell's equations, where he discovered the speed of light and therefore made light magnetic and electric. But I'm just saying.
You are aware that the mainstream.
Obviously I have a great deal of contempt for the mainstream
electrodynamics
interpretation.
maintains that there's a photon that explains the magnetic force and the electric force is explained by an exchange of photons.
I don't think they have a very deep or well-reasoned theory connecting photons to electricity or magnetism. They just say it. They don't actually show me any evidence of it.
Well, I'm not disagreeing on that point. I just want to know what you're saying, because I can't really understand what you're saying. I mean, if light is a photon, and you seem to be very definite about that, and you say it travels,
it's made out of a force. It's a force. It's a force. Light is a force.
So you're saying light is a force.
Just like, yes, just like gravity, just like magnetism, it's a force made of force bits.
All right. So now, can we talk about radio waves? Because we know a little bit more about how radio waves work. So you're saying that there's no electric field and no magnetic field in electromagnetic wave. Is that what you're saying, or what?
I'm saying they don't come off as a wave. When you create a radio signal, you're just releasing a whole bunch of photons all at once. So they all leave at the same time, and then you shoot out a whole bunch more at the same time. You shoot out a whole bunch more at the same time. They're individual bits moving in straight line paths. And the polarization of radio waves is gigantic. That is, you know, they don't line up as well as really lined up light. So the argument could be made that they're just rays coming off of the radio tower. And if we could see radio waves, we would see it much like we see a light bulb, the rays of light coming off of the radio tower. And yes, they're coming off at a frequency that can be much larger than the frequency of nanometers for light. So that's the only difference. So a light bulb is essentially doing the same thing. It's creating a ton of little bits, and then it waits a 700 nanometers.
Well, if there are no waves coming off, then how do you explain the bending of the radio waves by the ionosphere?
The bending, it's refracting, so it's interacting with electrons. It's an electron force that if its electrons affect it, so it scatters. Okay, some reflects up, some reflects down.
Electricity and magnetism. Okay.
Go ahead again.
Everything that we know says that Maxwell's theory, Maxwell, calculated the ratio between the magnetic force and the electric force. And they determined, came up with this constant C, which Maxwell said, oh, hey, that's interesting. This C that we get by calculating the ratio of the electric force and the magnetic force is C, which is the velocity at which we know that light travels. And so he speculated that light is an electromagnetic wave. So based on that fundamental, knowledge, how do you explain electric field and magnetic field, and what's the difference between them, and how does that produce a photon that goes flying off into space, as you say in a radio?
Nothing produces technically a photon. They're universal elemental bits. They never stop moving the speed of light. They can only be captured by matter bits. You can capture force. So that would be one distinction. You want to argue about the history of Maxwell, I would say that what you left out of the story of Maxwell was he came up with a speed for magnetism, the speed that magnetism perturbates. And that speed was the same as the speed of light. And that's what really took place, is that the two had the same speed. And so that he decided that he was going to make light electromagnetic to match the speed, because the two of them had the same speed. So the virtual photon that they speak of in quantum mechanics, Maxwell discovered the speed of that virtual photon, and then it was decided that now light is going to be called an electromagnetic thing. They could have done it exactly the opposite. They could have said, like I always say, it's the speed of force, because all the forces move the same speed. So we shouldn't be calling it the speed of light. We should be calling it the speed of force, because they all do the same thing. Okay, now for your second question, which I've already answered 3 times, but I'll try to say it again. I'm saying that the electric field is a magnetic field. Okay, it's created by the movement of the electrons, creates a polarization in the material that's moving the electrons, whether doesn't even matter how like I said, you can have free electrons moving through a cathode ray tube and they're still creating a little bit of an electric field perpendicular to their movement. And that always takes place when you move electrons. And that field, though, is basically a magnetic field. That is, it has a bias, and it will magnetize a piece of ferrous material put in its vicinity. So it has the same effect as the magnetic effect, the field. It's just a much weaker field, and it's oriented in a different plane than magnetism. Magnetism is completely spherical. That is, it comes out of the whole magnet, where an electric field can be constructed in certain dimensions or planes that it's emitted. So it's not emitted in the same, it doesn't always obey the inverse square law. But they're fundamentally made of the same particles that are being exchanged by electrons. They're bouncing off of electrons. Electrons are repulsive because the force bounces off between it. So if you can think of it as two ping pong paddles would be, if two ping pong paddles are two electrons, and I have a ping pong ball bouncing between them, you can sort of understand as I move the ping pong ball, the paddles closer to each other, the ball hits the paddles more times per second. Therefore, it has more energy. And if I move the paddles far apart, the number of times the ball hits one of the paddles goes way down. So if I have the ball moving always the same speed, you can sort of understand that it's always the same force. So every hit is exactly the same amount of energy. And so I have more hits when they're closer together. That means I have more energy, and I have less hits when they're further apart. So the force, the electron force, bounces off of electrons. The proton force bounces off of protons. That's creating the repulsion. And the attraction is created because when a proton force hits an electron, it leaves perpendicularly, and therefore no reflections take place, therefore lower pressure, therefore the two objects will move into each other.
I want to take a moment here to just give a chance for anyone else who would like to ask a question or make a comment to do so. We have had lots of questions from Harry and myself and from Jack, but
and I do appreciate it. I appreciate it. So I thank you for the questions.
Jack Kirkendall, Franklin, I just sent you a copy of Professor Carnarev's work on electrons, protons, and photon absorption and emission. It actually shows his model of how this happens. If you could open that up and bring that image up, it would be interesting, I think, for people to see Professor Carnarev's work.
All right, let me see. Now, let's see. What is his basic thesis here? Photon absorption and emission. So let's see here. I'm sharing my screen currently. Can you guys see this? This is an AVI. This is a video. Is that what that is?
AVIs are videos, so yeah. But
I don't know how well that's going to work across things, but let's see.
Sometimes
let's see if I can play it.
You have to have a plug-in for that.
Okay, can you guys see that? It's playing a video.
Yeah, I got a blank screen.
You got a blank screen. Let's see here. So he's got this model that's got like rings and cones kind of thing, right? Is that what you're looking at, Jack? I might be able to bring it.
The green rings are electrons. The blue rings are neutrons that are in the middle. The protons line up. In his model, all the neutrons are in the middle because they have nothing but magnets, and that's the strong force. They all pull together. The protons line up with the neutrons magnetically, and then the electrons line up with charge. And it's the magnetics that keeps the electron and proton separated, and the charge that keeps them together. And the magnetics is stronger than the electric, and this is why they don't combine. And he shows the absorption and emission of photons by the electrons. And so I just thought you might like to see someone who has a model of how this actually happens.
So this model, you think, is the actual happens model.
It's Carner. There it is. It's Carnerev's model. I'm just presenting it because it makes sense. It's very logical. The green ones are electrons, the white ones are protons, and the blue ones are the neutrons. And this is a nitrogen atom. And when they absorb photons, they and it shows that photons are particles, and so the mass, radius, and frequency changes when it gives off one. The mass, radius, and frequency reduce. It's just a model.
Why are they quantized then?
Huh?
Why are they quantized
he has
in this
exact
model?
formulas for all of it. He has exact formulas for everything in all of his theories.
Well, formulas don't explain, physically why because Balmer's formula explains explains the quantization, but it doesn't explain the quantization. He's got a physical model here.
If you read his theories, you'll see that they do.
Well, I have a related subject, if it's okay to just broach it. They often talk about the energy levels inside of atoms, and they'll talk about how it takes more energy to jump to a higher orbit. And my argument would be, I think they have that backwards. I think the interior orbits have the high energy and the external orbits are the weak energy orbits. So I don't even think they have that model. I think they have it exactly backwards, like they have the plus and the minus sign wrong. I think they have the idea of where the strongest pressure is in the inside. The inside orbit is the high pressure orbit. The outside orbit is the low pressure orbit.
There are a lot of problems with even
I disagree with that. It's very simple. If you absorb a photon, you've gained mass, and when you gain mass, your frequency increases and the radius goes down. You have a mass, radius, and frequency, every one of the photons, which is what you were talking about. And when you absorb a mass, your radius has to decrease, the frequency has to increase. And so no, this model is exactly correct.
No, I disagree. So yeah, I don't believe there's any set frequency inside of an atom. There's just the ping pong paddle argument. The interior electrons are close to each other. That means the force between them is bouncing back and forth very fast. So that's where an X-ray would come from. The outside orbits are very far. The electrons are far from each other. That means they're producing very little reflections back and forth, and that's where your radio wave would come from, or some other long frequency.
I just thought you might find this interesting, and it's a model that is very logical. Thank you.
Okay.
All right, and I think you're both wrong, but it's okay.
Yeah, I'm not a big fan of things being round. My theory basically is, everything's, whether the little bits are square or triangle or round doesn't really matter, but they're certainly not cone shaped. There's nothing that has an extraordinary shape. So
I find the cone shape kind of hard to swallow myself. What is logical about that?
Those aren't cones, those are toruses, and he's just simply showing how they connect magnetically. The cone part doesn't exist.
Well, how about the toruses, huh?
Well,
I'm famous for saying that toruses are the worst thing that ever happened to science, so that's...
Yeah, I'm not a big fan.
Those make sense.
Hyperboloids and toruses, but yeah, there's a lot of them out there.
I'd say I don't know what an electron is, but I'm pretty sure it's not a torus.
Well, I'm pretty sure it's a clump. I think it's a clump just because it gets hit by clumps. So it seems pretty obvious that it's a clump.
Well, it's definitely some kind of distinct object of finite size and can be localized in some place. So yeah, I suppose a clump would be one way of saying, giving it that physical realization without really saying what it is.
It's definitely there, and it's not over there. It's just got a place.
Yeah, it's got a there, it's got a not there. We can see them in cloud chambers and what they do.
Well, you're not really seeing them though. You're really seeing,
We're seeing the
photons.
results, right?
Yes, I know, but you're seeing a pretty indirect byproduct in the sense you're seeing the photons released by the electron hitting ions, which is, pretty distant from actually seeing the electron. But I get your point.
Mm-hmm. Yeah, I'm not sure we've ever seen an electron.
Yeah, we haven't seen anything. Actually, we don't even get to see photons, really, right? You see them by
I
absorbing.
mean, we've seen things like atoms, but those pictures are generally speaking created by using electrons. But
Well, and those are also synthetic images. They're made by computer algorithms. They're not actual images.
I suppose there'd be some kind of debate on that. But
Well,
I get your point.
The best resolving power we have is the electron microscope. Obviously, an electron microscope can't see electrons, so it can't really, it can't view itself. You know what I mean? You can't reflect an electron.
And I'm now talking about electrons. I noticed you have lots of videos.
Well,
one of them is spin.
But I just mean that the atom, the only part of the atom you can bounce something off of is either the electron or the proton. The atom doesn't have a membrane. So I guess I would just say that you're still stuck. Your view of the atom is still going to be an image of something that isn't going to be a round ball because the atom isn't a round ball. It's obviously made of little bits in positions.
I would say so. But I was curious about your opinion on spin, since we're talking about electrons. So do electrons have spin, or what is your opinion on that?
Yeah, I think spin is manufactured by, modern physics. They don't even have a definition. They don't even really know whether it's actually spinning or not. And it's just a way of identifying the changes that take place in charge when you move particles. They're charge changes. So no, I don't think anything really spins, and I don't think spin is a real concept. I just think the manifestation of a change in charge is a manifestation of a change in velocity.
Well, then I would say we're probably in full agreement on that one. Yeah, spin is a bunch of hooey.
Yeah.
I see you have lots of other. Let's see. Let's go back to your website here. And you have a lot of talk physics here. So you apparently have your own physics show that you do.
Well, it's not much of a show. Yeah, I just read my snarky comments that are quite horrible, and I just argue with trolls mostly. So yeah, I'm trying to get some people who want to actually talk about the physics to come into the room, but it hasn't so far. I haven't been able to do that. So yeah, I just defend my theory against people who just ridicule how funny looking my hair is or something.
Well, hopefully we haven't ridiculed your hair any.
Yeah, no, I guess I really do appreciate it gets a little hostile in here, but it's really quite under control, and I really do appreciate being in. The only way I can explain my theory is to have people tell me what they don't understand. So I really appreciate understanding what you don't understand. I appreciate knowledge of that anyway.
Yep, that's what we do. Unless you want to have a knockdown ether versus not ether fight, right? Maybe we'll do that at the conference.
But I mean, it's just the kind of thing where, yeah, you have to do it under rules of some kind because, you're already, you're going to accuse me of having a prejudice, and I'm going to accuse you of having a prejudice.
I mean, but that's okay. And I've never been able to change anyone's opinion of their pet theory anyway. So, I mean, what do you think about that? I mean, I've never met someone where they said, oh, I don't believe in the ether. And then you talk to them and they go, oh, okay, I think that makes sense. This never happened. I don't think it ever will.
Yeah, I can't say it never happens just because I think I have persuaded a few people that I'm onto something. So I think I have gotten somewhere. But yeah, this is a lot tougher than I thought it would be. I thought I'd do this for like 6 months and I'd get a Nobel Prize and I'd be done because, I got a unification theory. This is all really simple. I said, wow, and it's 7 years now I've been arguing this stuff, and it surprises me how belligerent people are and I guess it would be okay if they were belligerent because they really understood what they we're accepting, but they're just accepting it because Feynman said so, or they're accepting it because Einstein said so, and they really haven't analyzed any of it themselves. And that's the part that sometimes is, quite depressing, is you're just being basically told the Pope is God's messenger on earth, and I won't believe otherwise, and it's like, I can't argue with dogma.
Well, I think me and Bill are still waiting for our Nobel Prize too. It's quite disappointing they don't come rushing to our door. I think you'll find that's actually quite common. I think that was one of the things that there was the book, and they said everybody kind of get this Jesus thing where they think they're going to save the world, and no one comes rushing to our door to hand us our Nobel Prizes, even though
the difference is the difference is I'm actually right. So,
yes, that's exactly what we all say.
Yes, I mean, it's just so obvious that I'm.
The reason why you haven't gotten your Nobel Prize is because they haven't gotten to my door. So
I'm so much righter, and you guys are just making noise. You're getting in my way. If you all shut up, then I could make this clear, and everybody understand what I'm saying. But yeah, it is funny that it is tough being.
I assure you, we all exactly think that same way. I hear you, man. Except that I'm the one that's right. Right?
Yeah.
So I have a comment on this conversation.
Uh-oh.
Go ahead, Harry.
Well, one view of science is that the reason that official science, I'm sort of thinking I like the term official science as opposed to mainstream official science, because that sort of implies what Gary was saying, which is they're right because they say so. That makes it official science. But their real main claim to fame is the idea that they have produced all of the technological marvels that have been so beneficial to mankind. So my comment would be, if your theory can be used to invent some great device, some tremendous technological invention, like you can produce energy, with no smog, no pollution, no nothing, and you could just produce energy and it was safe and marvelous, then your theory would be accepted, because the real reason that science is accepted by the public is because it's useful.
Yeah, it is unfortunate. Truth doesn't matter, but you could say that about a religion. Religion has these positive effects on people, and it gets them through tough times and all this stuff. But you could also argue, yeah, it's really divisive and it's absolute bullshit. So why endorse it? Because it's getting the right answer for the wrong reasons, that kind of thing. And it is really kind of obnoxious to the idea of science, though, to make all these declarations that they've made, that they've proven something, when their proof is incredible. I mean, I keep coming back to that argument. It's glaringly weak evidence. I mean, the evidence for gravitational lensing, incredibly weak. The whole two-slit experiment as the foundation for all quantum mechanics, incredibly weak evidence of Huygens or Heisenberg or any of this stuff they claim to be these real effects. The very fact that they rely on a virtual photon, I mean, it's almost a laughably vacant explanation, and they get away with it. And they only get away with it because, yes, they're smart and they have degrees, and they're claiming that somehow without them, somehow we wouldn't have figured out how to invent a wheel. Of course we would have figured it out without them. I didn't need quantum mechanics to figure out the round thing works better than the square thing.
Yeah, but the point is that they have a group, and the group has an ideology that's defined by the group, and this ideology that defines the group claims that they have provided all of these tremendous benefits to mankind. And so they sort of wrap themselves in the whatever the group says is true because the group says so.
Yeah, I just don't think one of our theories, a theoretical change isn't going to change the fundamental physical laws. And so they have the fundamental physical, what the byproducts of experiments, they have some of that right. They just have the definition of the causes wrong. And so I don't think any of us are going to be able to create some better way to do nuclear fusion or something. We're not going to be able to, through theory alone. So I just don't think there's going to be any Tesla magic here that you're going to, figure out how to tap the ether or any of that kind of stuff. So if you're waiting for that to happen before you can disprove them wrong, then no one will ever get disproved. But yeah, I think that I just look at it as a court trial, and I say, if there was a fair cop, if there was a fair judge, he'd know this is junk evidence that they're presenting in this courtroom. And that if we
Well,
had
I think the
between the dissidents and conventional science, if there was a fair contest, we could win. And I think what we have to do is all of us collectively is come up with our individual really pointed questions that get to the root of their corruption, and force them to answer these questions they've left unanswered.
Well, I think Harry makes a good point that no one's going to believe us until they can, levitate your car or present a little square box that just generates energy out of nothing based on your theory. So, and that's in some ways, I think that is perfectly fair, right? I mean, what would be the point of a theory that just re-explains everything that we already know, right?
Because it's the truth.
That wouldn't help. Even if it's the truth, it wouldn't help us.
I know, but you could argue that what's the point of evolution then? You're not grateful to have knowledge of our actual origin, that you don't appreciate having that knowledge and not being ignorant and thinking Thor is making lightning and stuff. I'm very grateful to know the truth and not be stuck in some ignorant notions about boogeymens and hobgoblins.
In some ways, you got to wonder about, well, are we doing science or science fiction? Because a lot of what we do is extremely speculative, and a lot of what I might be talking about could be considered equivalent to science fiction. With no reality. In fact,
I don't feel that about what
I should be. Let me finish talking one person at a time here. Okay. One person, at least let me finish my sentence here, right?
My apology.
So, try to not speak over other people. At least let them finish their sentence. Okay. So I was saying that, there should be some practical implications of your theory. So, for example, if I say gravity is just the electrostatic force, then it should mean that for people like Elon Musk who are trying to send rockets into space, that I should go tell him, go charge your rocket up positively, because that would be the opposite charge of the Earth. And therefore, you will be able to use it much less fuel. Getting your rockets into space would be, say, a practical application of your theory, showing that it is correct, because it would be predicting things that are not currently predicted by mainstream. This is why if your theory only predicts things that are already known, then it could potentially be wrong, because you're not coming up with any deeper explanation. So that would be
I guess kind of disagree that like I said, I think the fundamental laws have been established, like the inverse square law, the function of charge, things like that. And their definition is so well established that I don't think you can rewrite that part of physics. So if you don't have an explanation for charge and you don't have an explanation for the inverse square law, your theory is probably not going to work. And I don't think it's going to be competition for them. So I think you have to cover those things that are really known from really good evidence. I'm just saying that a ton of physics is based on really weak evidence, and that's the real distinction. There's really strong evidence and there's really weak evidence. And you have to make a distinction between the parts of physics that are arguing the strongly evidenced declarations and the very weakly evidenced declarations.
Well, I think, for example, you talk about charge. Now, if your theory says exactly what charge is, then that would open up the possibility of, say, making a charge gun. So something that you could just turn on and would immediately replicate the charge of like a 1,000,000-volt object in the room or something like that. Be like...
Well, you can only make a charge gun by doing the same thing you do with any other force. You have to segregate the force. That is, you have to create a propellant of some kind. You have to create a fuel. So you can't get it for free.
Well, no, I mean, let's say I believe charge is an electromagnetic field. So all I have to do is create some device which creates that frequency. And if I could do that, then that would give a lot more credibility to say my theory. Because
yeah, you make a believer out of me. Yes, you make a believer out of me, but I don't think you're ever going to do that. So I don't think that's a viable way to demonstrate your accuracy. But fine, that's the Tesla thing. I guess you're.
Well, that's Harry's point, is that we need to be, our theories need to be do something practical, right? I mean, if I could create like something like a speaker, but instead of generating sound, it generates a strong electrostatic field. That would be amazing, right? And then, then they would give me my Nobel Prize. Then they're not going to give me a Nobel Prize just for saying that electric field is
I'm just saying all
magnetic field.
I think those things, if they were discoverable, they would have been discovered, kind of thing. It's just not I don't think you're going to make any leaps in discoveries. I think all the
I think you underestimate the stupidity of humanity.
Yeah, I worked in a machine shop. I'm just saying I kind of know what experimenting is like, and I know that this isn't 1910 where everything isn't invented yet. It's 2018, and everything's already invented. It's a lot harder to find any new physical fact.
Well, I got a question for you.
Go ahead.
On this issue of a new physical fact, and I tend to sort of agree with Franklin to a certain extent. My question would be,
you do? That's the first time in it.
Yeah, right.
Go ahead.
Well, as soon as I hear this argument, the main thing that Franklin said that I agree with is, I guess it was sort of vague, but he said that maybe some things are completely wrong. And one of the things that I think that they're completely out to lunch with is superconductivity. So I would ask, in your thinking, Gary, what do you think superconductivity is, and what is it about?
It's just about getting rid of the heat. The heat creates noise in a system. So it's like a magnet. Magnets are really vulnerable to heat. So as you heat them up, the domains start flipping in different directions. That is, the atoms start moving in different directions, pointing in different directions. So it loses its coherency. So the pattern is broken. So superconductivity is all you're basically doing is taking a conductor and you're taking all the noise out of it and making very straight pathways for the electrons and the force to travel through. So you're basically taking all the vibrations out, all the crooks in the road, all the strings that aren't straight, you're taking all the junk out and you're making it really clean. And so now you can shove a ton of voltage through it because it's not hitting, it's not creating scatter. So it's like looking at a pure blue sky in a clear atmosphere. It's like there's no scatter, there's no crap, there's nothing in the way. It's just this, which isn't actually true about the atmosphere, but I'm just trying to make the point. It's a really clear view versus a foggy view. So in irregular heat, it's foggy inside of a conductor. When you make it really cold, it's really clear inside the conductor.
Well, that's an interesting idea, but superconductivity, as I understand it, is defined by the Meissner effect.
Well, I'm just saying, I think the effect is basically what I just said, which is the atomic structure becomes quiet and very well aligned.
Now, what is this Meissner effect that you're talking about, Harry? Is that the one that causes the magnets to levitate?
The Meissner effect is supposedly that the material ejects the magnetic field entirely. So if you apply a magnetic field to a material above the superconducting temperature, the magnetic field penetrates the material. And when you cool the material below the superconductivity temperature, the physics of the magnet of the structure is such that it, quote, expels the field or repels the field. And
Right.
that supposedly is the hallmark definition of superconductivity. So actually the word superconductivity is sort of doesn't really define the phenomenon according to what the physics say. This is all very confusing if you ask me.
Yeah, well, so I would compare it to like say if I could make the atmosphere very lined up, the ions really line up perfectly straight, so nothing got scattered, and the electrons wouldn't even have to move. The force would hit one electron, and its force would vibrate the next and the next and the next. So essentially, the electrons don't actually have to travel anywhere. They're just conveying the ping pong paddle force. So let's imagine 10 ping pong paddles with balls bouncing between each one, and the pressure from one end would get to the other end really clean. So if we could do that in the atmosphere, then the lightning bolt would be invisible because it wouldn't shoot any photons. It wouldn't make any, it wouldn't have any, it wouldn't burn anything in the atmosphere. So there would be no physical consequence. So the lightning bolt would go invisibly straight, and it'd be this incredible amount of transfer of power. And so that's what I would compare it to. So it's when you make the alignment, then yes, you're not going to create the perpendicular secondary magnetic field. You're not going to create the eddy current that's going to disrupt, that's going to create the opposite effect, which means the thing is going to keep wanting to flip over. So you're preventing that flip mechanism, which means that's why you can levitate the magnets, is because they don't need to flip anymore, because you're not creating another magnetic field that's in opposition to the one that exists. So you have no.
So along with it, anyway, to make my point would be if you had a theory and you, based on using your theory, you were able to make a room temperature superconductor, then that would be something that would really shock the scientific world.
Well, I think if you did that, though, that would just be a kind of alchemy. You're just going to be mixing different elements together to try to create something that duplicates that lack of heat condition, which is lack of noise condition. And there are room temperature superconductors. There just aren't too many of them. So it's very rare elements.
Well, they're not that good at conducting electricity, apparently.
Exactly. Yeah, they're super insulators or something.
Well, I mean, I have some thoughts on that, because see, the thing is that all magnetic fields must be created by moving electrons, and you have got these permanent magnets, and so that kind of implies that there are permanent electric currents running around in there, and if there are, those would be superconductors. So my idea would be that there must already be a piece of iron, a magnet must already be a room temperature superconductor, but it's just that electricity doesn't flow across the magnet. And in fact, your best magnets are insulators.
Yeah. And, okay, go ahead.
And the reason why your best magnets are insulators is because you don't want the electrons leaking outside of their superconducting loops. If they did, then that would decrease the magnetism, and that's why. But in order to create a room temperature superconductor, is that if you could somehow take your neodymium magnet and actually make the size of the loops really, really big enough to be the size piece of conductor, then you might potentially have a large superconducting macroscopic object that could be used as a practical superconductor.
I don't think neodymium magnets are actually pure neodymium, so I think pure neodymium is conductive. They're a ceramic, they're composite.
Yeah, they're a ceramic. They're totally, they're closer to rock than iron.
So. But I'm just saying they're not the pure element, so that's why they're not conductive. Just like ferrous materials are doped iron, so they're not pure iron. That's why they're not conductive. So I don't think those two are connected, and I certainly don't think there's any currents inside of magnets, perpetual currents running through them. So I don't think you ever need an electrical source. So again, you're doing the electric universe thing where everything's electric, and I'm doing everything's magnetic. And the only thing the atoms are doing is filtering the force that comes in. So they don't need to move, and they don't move at all. The magnet has no movement inside of it. It's just directing the force. The force moves through the magnet and gets filtered. And it's that simple. There isn't any currents moving through it.
well, then you would have to have two distinct ways of generating magnetic field. So the way that the magnetic field is generated by a loop of wire, you're saying is totally different than the mechanism as done by a permanent magnet.
Yes, exactly. I mean, it's different in the sense that it's an alignment issue. So we're just talking about the geometry of the atoms. And so the magnet, the geometry is set by magnetizing the material. That is, the atoms are put in an arrangement and they don't come out of it unless you whack it with a hammer or something to disturb them. And in the conductor, it's happening only temporarily in the sense that while there's a current flowing, the electrons are biased to the protons. The protons are pushed down, the electrons are pushed up at one end, the electrons are pushed down, the protons are pushed up at the other end. And so you're creating a geometry of the atoms that duplicates a magnet. So that's why it becomes weakly magnetic, is because on the surface of the conductor, you have created essentially a segregated geometry, and therefore it behaves like a magnet while you're moving the electrons.
Well, that could be true, but I think it's wrong. But like I said, that's okay. But the thing is that it's not that your explanation doesn't make any sense or there's anything wrong with it. In fact, it could be perfectly plausible. It's just that there are other explanations, like, so let's just compare and contrast. Now, it's either that the atoms themselves act as miniature magnets, or it could be that there are these superconducting loops inside of this permanent magnetic materials. That's the two possible things. Now, so the question is, if you're a judge and you're looking at these two things, so what makes one better than the other? That's kind of the question. Well, so I would argue, just a minute. Like I said, don't interrupt me while I'm talking in the middle.
All right. Well, you asked the question, so I always want to answer the question.
Yes, you can answer your question. So I'm just going to say that you have to consider things like the number of concepts required to explain any given thing. So I would tell the judge that, okay, if that's true, that they're superconducting loops, then the mechanism behind the magnetic field being created by loops of wires is identical to the mechanism that creates permanent magnetism. So you go ahead and make your point.
Well, I would argue. I'll let the other guy go. Go ahead. Sorry.
The issue is that the official physics really doesn't know how a permanent magnet works, although they would imply that they do. But if you look at the books, it's not very convincing, as you said. It's a weak explanation.
I mean, mainstream just explains that the permanent magnet has these small magnetic domains, and they're all act like just tiny magnets, and they're all aligned, and that's how the magnet works.
Yes, but isn't that how magnets work? If I break a magnet in half, it creates two new magnets, because that's how it's happening with the atoms. You can break it all the way down to the atom. So
but I would argue that
breaking the magnet and breaking the magnet and breaking the magnet, the domains are really a collection of atoms that are in one orientation. So they're all the domain is actually a magnet made of little magnets called atoms. So domains aren't where their physics stops. Their physics stops with the atom. The atom has the magnetic moment, and the atom is the thing with the bias.
Yeah, but I would argue that the magnetism is not found at the atomic level, because if it were, then basically any material could probably be a magnet, because all magnets are made out of atoms. But the best magnetic materials are made out of these composite crystals. So it seems to me that the smallest unit of magnetism are these domain crystals. And my prediction is that if you had a sufficiently sensitive kind of something, you would see that the superconducting loop is actually going around that crystal. It's a macroscopic. It's something which takes a large number of atoms in order to create permanent magnetism. So this is an experiment I would like to see. Like, just take your magnet and just make it smaller and smaller and smaller and smaller. And is there a point that, it stops becoming magnetic? Or is it still magnetic right down to the last atom?
Well, I think the ferrofluid is getting pretty small little bits. I'm just saying, so I think there's every reason to see that the evidence sort of indicates. I'm just saying that the idea that you have polarized atoms, in my opinion, is pretty solid theory. But if you don't think so, I guess I can't cite an experiment offhand, but I think it's pretty solid. Some atoms, because of their geometry, are different than other atoms. They have a bias because they have more electrons or less electrons. They have an uneven number. They have a lack of symmetry. A lack of symmetry in your number of electrons means you're going to have a chargeable atom.
Well, I have no disagreement. I mean, I have my own theory of atoms say that, you know, they look like this, and there's definitely can be kind of an asymmetry depending on, you know, whether certain things of it are filled in and out. But the question is whether, you know, something like an atom sitting by itself can represent a magnetic field.
Yes, if you think of it as a filter. So I'm just saying you have to think of the word filter and think that there's an actual force going in, and the force changes by the magnet changes that force, and therefore the force coming out is now different, and it's that difference that makes all the difference.
It's the difference that makes all the difference. Okay. Let's see here. We're getting pretty close to the end of the hour here. And we've just been having our casual discussion here with Draft Science about various subjects. And we've mostly been investigating and asking some questions and providing objections and alternative ways of explaining things. And that's all good. But I think it was interesting, that whole thing about, because we kind of joke about this, that, you know, as soon as you recognize that my theory is right, then, you know, then we can all go away. But
yeah, we can all find something. What are you
gonna do when that happens? It's like the dog who chased after the car. He chased and he chased and he finally got it, and then he's like, yeah, got this.
Yeah. Well, I'm a fairly good artist. I'd like to become a better one, so I could definitely go back to painting or do something else. But yeah, I'd like to fix the world and then go back to living my life. You know?
Well, I think Harry is right, though, that until we can show some practical application of our theory, or at least an experiment that clearly shows that we are correct. And you have to have these experiments that show that only your explanation can do it, and which would predict a contradictory thing from another theory. That's kind of the standard that we use.
Yeah, I think there might be a few experiments that can be done to do that. There's hope, anyway.
There's hope. I mean, we discussed this question about, you know, what light is, and I would agree that it is definitely a corpuscle, meaning that it has the particle-like property that it is
clumpy.
Well, yeah, it's clumpy. It has a finite size. It occupies a finite amount of space. I think the gamma rays that come off of these, you know, positron electron experiments pretty much shows that. Of course, as an etherist, I have to then explain what the heck that clump is, right? Because as an etherist, I think that particular gamma ray is a wave phenomenon. See, that would be my
that travels like
my burden to try explain that.
A wave traveling like a bullet, like in a straight.
Yes, a wave traveling like a bullet.
Right.
So, you know, for me, I say that, yeah, it's a wave packet. So it goes, it just starts, it stops, and what I do have to do some things, like say the special medium of the prop is that it's a lossless medium, so that it doesn't spread, because normally any wave you create will spread and widen, right? So, but the gamma ray clearly maintains its packet-like phenomenon, and probably it could travel for miles and hit the detector and still maintain its same energy. So, you know, as an etherist, I have to say that would have to be something that I would say postulate, right? That it's a non-spreading wave, but it would still contain a frequency. It would still contain a specific number of wavelengths. Although I think probably a gamma ray is probably just a single bump. So, and you could measure the frequency. But it is an interesting question. But I think, quantum physics answer, which is it's both a wave and a particle, is just silliness.
Well, that's at least one thing we can always agree on is they're wrong. So we don't know which one of us is right, but we know they're wrong. And conventional
but until
physics.
I can levitate my car, no one's going to believe me. So I'm going to work on levitating my car, and then I'll get my Nobel Prize. Until then, we're just going to have to just play with ourselves. So.
Yeah,
and it's our hobby, I do this for fun, right? It's like, okay, no one believes me. No one's going to believe me until someday someone actually figures it out, and then they'll look back and they'll say, because the person who gets the Nobel Prize is the person who first commits it to paper, right? That's why publish first is always critical, right? And they'll find all my papers, or they'll find your papers, or they'll find Bill's papers, and then they'll have to credit us.
Well, the great thing is I have 800 videos starting from the very beginning of the theory and building up all the, I didn't have magnetism in the beginning. I didn't have all the other, I didn't have a unification theory when I started. I was just doing gravity. So I have the whole thing, documented from.
So you'll just have to wait for some other guy finally in the mainstream to, figure it out. And then you can just sit back and get the credit.
Well, I think I have to make the proof, and I think I can. So I'm not going to hold out for a magic wand thing, but I think it's a reasoned argument. I think like evolution, you can reason through it and prove that, this is the right answer, and there's no boogeyman, and there's no hobgoblins, and blah, blah, blah.
Nah, Harry's right. I mean, you got to go and create the spaceship that can fly off into space without any energy, or the box that charges your iPhone with like nothing.
I know, but Darwin didn't have to do that. Darwin didn't have to provide a more comforting explanation of reality. He just provided a more truthful one, and took a while to defend it, and most of the world still doesn't believe it, but at least the intelligent people do. So I think you don't have to go with the gimmicks. You can go with just the truth and the facts.
No, I would disagree. I think I'm totally with Harry on this one, is that truth is not enough. If you think that's not enough, you're fooling yourself.
I think it should be for intellectuals. So I guess I'll just say,
but it totally isn't.
You called me a pessimist or something before. I think you're a horrible. You're underestimating the capacity of brains to do logic, to say that you can't ever make a logical argument that people will accept if they don't get a free lollipop. I don't think they have to be bribed into understanding the truth. I think you can.
No, they need convincing evidence, and so
convincing evidence seems to me is demonstrating how weak the evidence for quantum mechanics and bent space is. The evidence for bent space is preposterously weak.
All that does is prove previous theories wrong. That doesn't help you at all.
I think that's all I have to do to explain, because mine explains everything in a nice, rational way. No woo, no magic bits, no UFOs.
Oh, I think a lot of that is magical.
Well, I don't think there's anything magical about saying there's photons, that there's a bit in the universe that moves the speed of light. I don't think there's anything magical.
Yes, I think that's incredibly magical.
Okay, well, I think making up an ocean of ether that goes everywhere and does everything is also incredibly magical.
Really? We have oceans, we have air, we have things that's...
Yeah, there's no evidence that we have that the universe is made out of it. There's absolutely, we know what the ocean's made out of. We know that most of the ocean is empty space. We know that most of the ocean is empty space.
We have evidence that, we can pop positrons and electrons with pair production.
I'm not doing the pair production thing. That's more hokum pokum. So you might believe that, but I don't believe that.
That is an experiment. I mean,
well, I'm saying there's plenty of experiments you doubt the credibility of. I'm saying that there's no such thing as entangled particles. It's silly.
Yeah, entangled particles are silly. But I would say that there's definitely evidence that space is made out of positrons and electrons, because we can kick them out of seemingly empty space.
Well, I think that's a delusion, to think that they actually made something out of nothing. So, but whatever, you can believe it if you want.
No, but that's the logical thing, is that either you make something out of nothing, or the something was there before. I prefer to think the thing was there before.
You think the something there before doesn't make any sense. I think that making something out of a nothing is incredibly wooey.
Yeah, you can never make something out of nothing.
Well, that's what your positron blah 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 is.
No, it isn't. No.
You have insufficient energy to create what you're creating something that has more substance than the things that went in. So
no, that's incorrect. See, as an etherist, I say that there is a physical substance always in space.
I know. Well, I'm just saying the actors outside of the ether don't provide sufficient. You're creating mass or you're creating energy, and you can't do either.
No, you're not creating mass. As an etherist, all you can do is kick the mass out of the ether.
I just said. Well, let's not argue. We're finishing up, but I wasn't. I was arguing outside of your ether. The equation doesn't make any sense. If the ether.
Yes, the equation doesn't make any sense. I think we can totally agree. Mass into energy is a bunch of foo-foo. So that doesn't make any logical sense. Nobody. Whenever people say that, I say, okay, what is the mechanism by which that happens? Of course, they can't answer.
Well, that's not exactly what I said. I actually do believe that you can get force out of mass because matter contains force, but whatever. It's okay. Obviously, I haven't convinced you yet. More work required.
Yep, well, that's why we discuss things, because you give me your viewpoint, I give you my viewpoint. But like I said, the thing is that you probably can't find any logical errors in either our viewpoints. So therefore, neither of us are going to move off of our viewpoints. Now,
that either.
But if I were able to produce an experiment that shows without any doubt, and I'm not sure how I would do that, but if someone could do an experiment showing that there is a presence of positrons, electrons, C everywhere, even in a pure vacuum, perhaps some machine that just pulls it out, or maybe some machine which actually creates a wind of these things, so that just like trying to prove that the air that you're breathing exists, right? If I could pump it out or do something with it, then could prove it exists. Then that might be convincing to you, but I don't have any such evidence like that, so I'm not going to be able to succeed in showing you that that positron electron C thing exists.
Well, I'm just saying, I think it's still a logical argument. You're just basically trying to define the parameters of the checkerboard, and your checkerboard, in my opinion, is still funky. It's got all kinds of funkies in it, and mine is nice and simple. It's little red squares, black checkers, red checkers, simple rules. Yeah, no problem. So,
yeah,
but
anyway. You got all those checkers and forces in there.
There's only two kinds of force. There's only two kinds of matter. What's the big deal? It's not complicated at all.
Four things.
Wow, four elemental bits of the universe. Gee, I mean,
you need to bring it down to one.
Oh, I mean, that's just. I think it's silly because you can't make anything out of one thing.
Sure you do. I make everything out of one thing.
Yeah, well, I'm just saying you can't have any conflict. You can't have any. You can't get complexity out of a universe full of just one thing. There has to be things that fight with each other, or you have no complexity.
Yeah. See, so you have one thing. That thing is the matter particle, and that thing can be either a positron or electron. The only difference is the frequency at which it. The only difference is the frequency at which. The only difference is the frequency at which it resonates. You see, but it's exactly the same particle.
Yeah, I know. Well, mine was the
same
thing too. I'm just saying, but you're now giving them a distinction. So mine creates a distinction. I count for frequency being a distinction, but I also think polarization, you have to explain charge, and my theory explains charge.
Well, maybe one day we'll have to set up a judge, and then we're going to have the etherist and the non-etherist have a debate.
I think it'd be interesting to try the case to make the arguments about where we both have weaknesses and where we have strengths, and try to prove that one theory is a much more, but it's a lot better.
Yeah, maybe Harry can judge.
Yeah,
maybe Harry can judge.
Yeah, he likes both.
He doesn't believe anything, so
he loves it both so much.
Okay, well then I think that will do it for today's science chat. I thank Gary, Draft Science here, for indulging us in asking him questions.
I'm also grateful.
And but that will do it for this week. And I think probably we'll be taking a break for the next 2 weeks. We have the CNPS conference coming up, and although I might be broadcasting live on the 30th when I'm at the conference. So maybe I'll have a report on what's going on that date.
Yeah,
But
you have a website, right? live.naturalphilosophy.org, I think.
Yes. So if you tune in probably anytime between 9 and 5 on that live site, you'll probably see one of us blabbing away. So
Very
we'll
good.
see how that goes. So remember that, but probably just next week we probably won't have a science chat. All right. So that will do it. And I am signing off.